The next theorem in this section is called the mean or average value theorem. So remember, mean means average. So we're going to start with an example that you're probably familiar with, looking at your distance as a function of time. So this graph shows the distance from home in miles of a, that should say, car, person, whatever, after they turned right onto a road. So the first question, what is their average speed over the time interval 0 to 10? So we can see that we have 0, 0. So at time 0, they were at home, and then 10, 4. So 10 minutes later, they were 4 miles down the road. So part A, we're just trying to find their average speed. So we do the change in distance divided by the change in time. Our distance ends at 4, so 4 minus 0 over 10 minus 0, but we need units on that. So our units would be miles per minute, which is kind of a weird unit or a weird rate. So 2/5 of a mile per minute, which isn't super fast, but if we multiply that by 60 minutes per hour, we can get their average speed in a number that we're more familiar with. So this ends up being about, well, not about, exactly 24 miles per hour. So not very fast. Maybe they were going through a school zone, who knows. Okay, part B says, is there a place where their instantaneous speed is exactly 48 miles per hour? I think I meant for them to be going an average speed of 24 miles per hour, or 48 miles per hour. So, hold on. Yeah, we're going to go ahead and change this to 24 because I wanted to illustrate the actual theorem of the mean value theorem and not something else. What I'm going to do is I'm going to draw a line segment between the two endpoints, and we know that that line segment has a slope of 24 miles per hour, or really 2/5 if we look at it in the units we originally had. And if we think about how we know car travel works, if their average speed was 24 miles per hour, our law of averages said sometimes they were probably going faster than that, sometimes they were probably going slower than that. And in fact, we can look visually and we can see probably 2 places, it looks like, where they were going exactly 24 miles an hour. So they had the same slope as their average rate of change. So the answer is yes. So they probably went, in fact, we know they did. They probably went speeds above, below, and equal to 24 miles per hour. And we can see that just by looking at the shape of the graph. So they started going slow, they accelerated, they reached their top speed right about here. That's where my slope is the steepest. And then maybe as they were nearing their destination, they gradually slowed down until it looks like they're going a slope of 0. So that would make sense for stopping. We have to remember that a car can't just instantaneously reach a certain speed without passing through all of the speeds in between. Okay, part C says estimate their maximum speed. So the maximum speed looks like it's right there. So what we're going to do is zoom in. We're going to try to draw a better tangent line than what I originally drew. So I'm going to erase this extra stuff. And to draw that tangent line, I'm going to look right there, and then I'm going to pick another point pretty close by, and I'm going to extend this until I can kind of grab at a point that looks good to me. So actually, maybe it does hit right there. I'm going to say that it looks like it hits right there. Again, we're just estimating. So if I look at that place is at 6, 3, and this was at 5, 2, and so it looks like our slope is about 1 mile per 1 minute, and maybe you recognize that as being 60 miles per hour. So it looks like if I'm looking at the instantaneous rate of change at time 5, it appears to be about 1 mile per minute or 60 miles per hour. So let's take a look at the actual mean value theorem. So the mean value theorem says if your function f is continuous on the closed interval a to b and differentiable on the open interval a to b, so again it's continuous, but then it's also smooth, there exists a number c between a and b such that f prime of c is f of b minus f of a over b minus a. So what is this really saying? This is saying f prime of c is the instantaneous rate of change of f at x equals c. So this is saying there's somewhere where the instantaneous rate of change of the function at c equals the average rate of change of f over the interval a to b. So this is saying the average rate of change is going to equal the instantaneous rate of change for at least one number in the interval a to b, so long as your function is continuous, that's important, and differentiable. So Rolle's theorem is actually just a special case of this. So in Rolle's theorem, your f of b equals your f of a, and so f prime of c would end up being 0 over b minus a, which is just 0. So Rolle's theorem is really just a special case or just a subset of the mean value theorem. Remember, Rolle's theorem was saying if you had function values that were equal at the endpoints, there was somewhere in between where the slope was 0. So a lot of what you'll be doing with the average value theorem or the mean value theorem is just showing that you understand what it actually means. So figure 1 shows an illustration. What I've got going on here is I've got a secant line between 2 points. So you can see those points that are marked right here. So I drew a secant line. Remember, a secant line, you just connect the 2 points with a straight line. And then right here, we've got this place where we've got a tangent line, and that tangent line is constructed between the endpoints of that secant line. So the secant line, it's hard to see, but like here's A, here's B, and then this point right here, C, where the slope is the same. So this is my tangent line. And it's constructed at some point in between A and B. And again, just like Rolle's theorem, it doesn't tell you where to construct it, it just tells you that it does exist. So let's see an example. We have a function f, we have some marked points A and B, and we want to sketch the secant line between the 2 points. So we'll start by just connecting them with a straight line. Let's see if that goes straight. Nope. Okay, that's as close as straight as I can get in this program. So that's my secant line. And then we're going to sketch any tangent lines that are parallel to that secant line. So it actually kind of looks like that tangent line right there is parallel. It looks like about right here-ish there could be another tangent line that's parallel. And then also somewhere up there. The easiest thing to do is if you have access to a ruler is just line your ruler up with the secant line and then just kind of move your ruler up and down on the function until it looks like you have a tangent line that's parallel. So we've got 3 different c values. We'll call them c sub 1, c sub 2, and then c sub 3.